my wife would tell me, would tell you I probably don't need a microphone, but is that on? Can everybody hear it? Yeah. Okay, good. And Abe, thank you very much for those very kind words. I wish I had that on tape. The word, the word, because I want to share it with my wife. You know, Andy and brain doesn't usually get used in the same sentence in exactly that context. But yeah, I want to tell you, I'm really excited to be here. Thank you very much. You know, Warren and I have been spending, well, we actually, Warren and I have been friends since 1986, 87. I mean, almost, what was that, 25 years. I mean, Warren and I, so, and Warren actually, you know, I was Warren's customer. He was actually making photoresist down in Fishkill, New York, because IBM was in the business of making these advanced photoresist products, and we were actually using them on our photolithography process up in Burlington, Vermont. So Warren and I spent a lot of time together back in the 80s, and he still talks to me. So photolithography. Now, who attended the presentation on RF plasma and etch? Okay, good. Because, you know, again, that was I wasn't here for that, but I read the presentation. I thought it was very well done, and you know, that kind of set the bar for our presentation here. Photolithography. Who's kind of studied it already in their classroom work? Photolithography. Okay, because we're kind of assuming that there's a little base level of understanding that we're going to build upon today in this presentation. Okay, who knows photolithography is not spelt with an F? Okay, good. All right, good. So, you know, we're doing this work over at CNSC, the College of Nanoscale Science and Engineering. Usually when you tell people that you work at CNSC, they'll go, huh? But if you tell them the ship, you know, the ship over on the corner of Fuller Road and Washington Avenue. So Warren and I have been working together for many years. He's the vice president for advanced technology business development at the university. He's got a very big, important job, and he's got an awful lot of experience in photolithography. So what we're going to do is we're going to break this up into two sections. First of all, because I couldn't imagine anything more painful than listening to me talk for an hour and a half straight. So we're going to break it up. I'm going to talk about the easy stuff, and then I'm going to turn it over to Warren to talk about the tough stuff. So we're going to talk a little bit about the College of Nanoscale Science and Engineering, kind of an overview, this idea of what we do at the university. Talk a little bit about Moore's Law. Got quite a few slides on Moore's Law. We're going to kind of try to make it easily understood. We're going to turn it over to Warren. He's going to talk about the photolithography process. And I'm going to come back up and kind of wrap up with this discussion about NEATEC and how the NEATEC and CNSC work together on this very exciting program that's funded by the National Science Foundation. And then we're going to have plenty of time for Q&A. We're yours till at least 11:30. So thank you again for your attendance. So, CNSC has survived 4 governors now. Republican governors, Democratic governors, doesn't matter. They love what we're doing at the college. So this is a very good thing. Most recently, Governor Cuomo. Everybody saw Obama was visiting. Warren actually gave a tour to President Obama in the clean room, walking around. I mean, it's very exciting what's going on at the university. So if you look at the corner, you can kind of see the ship. There's a laser on this, I think. You can see the ship on the corner of Fuller, and so sequentially, the building was built in 1997, and it housed a 200 millimeter facility for doing research. Next up in 2004, the NanoFab South building was constructed. In 2005, the NanoFab North building was constructed. This is actually when I moved here from Austin, Texas. In 2004, I actually was starting to work in this building. I was on my 3-month temporary assignment. That's 9 years ago. Never went back to Texas. Too much stuff going on up here. The NanoFab Central and the NanoFab East building were both constructed, I believe, in 2009. We actually sit. Warren sits over in this building, in the south building, and I sit over here, right about there, on the second floor. So we built this office building and this new clean room expansion. And you can kind of see the most recent development is the NanoFab. Everybody seen this building when you drive down the, okay, huge, huge building. Biggest building on site. Lots of plans. We're going to talk a little bit further about that in a couple minutes. But you know, this is a project that literally moved the highway. Remember Washington Ave Extension? Washington Ave Extension is now over here. Moved the highway to create space for this building. I mean, that's how much the governor is vested in the CNSC facility. Kind of impressive when you think about it, moving the highway. So the summary, $14 billion on that site. $14 billion, that's a lot of money. You know, there's a lot of clean room space, lots of room for tools, lots of room for experiments, lots of room for scientists to go to work and have fun. But only $1 billion of it is New York State money. So think about it. If you build it, they will come. $13 billion worth of stuff was brought in that was not paid for by New York State. You know, built the facility, attracted all these different partners. Everybody, you know, $13 billion, not New York State taxpayer money. The $1 billion was used to attract all of that business. Manufacturing tools in the semiconductor industry are expensive. You know, the little shiny box in the corner, $3 million probably minimum price. Very few tools under $1 million. But average price, you know, for a small tool, $3 million. We have a tool that's coming in to the NanoFab X building, $150 million for one piece of photolithography equipment. That's a lot of cash. And the thing that's been done here, the state has put this infrastructure in place, and it's attracted all these different tool suppliers that bring their individual specialties to, and they want access to everybody else's specialties. So, you know, one company can come in and can leverage this state-of-the-art tool set that CNSC has assembled. So, you know, you don't have to go out and spend $8 billion of your own company's money. Somebody else has brought, you know, the idea is that there's this collection of tools that everyone that's there can share and use, bringing down the cost of our research. It's a very, very interesting concept, very, very unique in the world. And every partner, including Semitech, my company, we leverage that tool set. We bring some tools, we leverage everybody's tool set. So it's a very good business model for getting a lot of work done. But what do we do? What do we actually do at the university? So what the crux of our research is Moore's Law. We're trying to make things smaller, we're trying to make things faster, we're trying to make things cheaper. So I brought an assembly here, you know, when you got a chance, have a take a look. 200 millimeter wafers, 300 millimeter wafers. That bad boy. We process wafers 25 at a time. This weighs about 6 pounds with this full wafer roll. 25 wafers, 6 pounds. This weighs 21 pounds, a box full of wafers. 68 pounds. Don't have to go to the gym anymore. 10 curls in the car. You know, again, I mean, it's literally, people can't lift those scoops anymore, the carriers for those wafers. It's all automated. We're using carts. We're using overhead transport robots. Nobody picks up those wafers. So what do? We're researching what do we need to do to make wafers bigger? And then we also work on how do we make wafer devices, how do we make chips smaller? And we want to basically fit more chips on a wafer. If they're smaller, for example, if you got my big old thumb on a wafer, how many die? How many individual thumbprints can I put on a piece of silicon? You know, a couple. If that die is smaller, like my pinky or a baby's pinky, we can get even more die on that individual wafer size. So without changing the wafer size, I can get more die. By changing the wafer size, I could get more die. So that's basically the idea, is to get more and more chips on a piece of silicon. So as far as bigger wafers are concerned, it's a pi r squared thing. 200 millimeter, 300 millimeter, 450 millimeter wafer processing. You know, there's roughly, every time you do a wafer size change, you get 2.25 times more area to put die on, just by changing the wafer size, everything else remaining the same. You know, this is one of the #1 reasons why, you know, we're increasing our throughput and we're reducing overall manufacturing costs. Remember, Moore's Law, we're getting things out, making them less expensive. You know, and if it's less expensive to manufacture, if you're, you know, again, it's economics. If I'm the only guy that can do it, I'm not going to pass the savings on to you, but if my competitors can do it, the price of those chips come down. But if I'm the only guy that can do it, you're not going to pay less. But, you know, it's economics. So everybody could see this progression of wafer size and what it affords. This is what drives that big building. Two things. One is 450 millimeter tool processing is going into this building. The other one is next generation lithography tools. That $150 million tool we talked about is going into this facility. Again, predicted to create 1,000 more jobs for engineers, researchers, scientists, and technicians. You know, lots of jobs for technicians. I think between what's happening up in Malta, what's happening at the university, if you've been reading in the paper, there's talk of another fab coming into the area that hasn't been assured. There's thousands of technician jobs that need to be staffed. You know, that's why Hudson Valley Community College has this program. That's why NEATEC was very interested in coming in and helping out develop curriculum to prepare you all for working in these industries. Very exciting times. Good place to be for a technician in a community college right now. So Moore's Law, Gordon Moore from Intel. It's actually, you know, it's not like a law, it's just kind of more like an observation. You know, in 1959, this is what a planar transistor looked like. 764 microns. I mean, that's almost a millimeter in size. I mean, obviously very visible to the naked eye. You know, these things were huge. They were, you know, they had actually put 8 of these on a single package because they only expected 6 of them to work. So they had redundancy built into it. So they could wire in, they could, you know, 6 of them would work out of 8 probably, so they could have their transistor count, built redundancy in. 65 microns, so basically the thickness of a human hair. These layers had to align to each other. If they didn't overlap by 65, you know, the circuits would be shorted out. Relatively large number. And it was a pretty simple manufacturing flow. 2013, these things are microscopic, I say nanoscopic. And again, we're talking 22 nanometers, 0.22 nanometers in size. These are tiny, tiny, tiny dimensions. There's billions of circuits on a die now. Overlay, the amount of tolerance you can have to be off, misaligned in X and Y, 2 nanometers, or it doesn't work. Very complicated, very, very challenging. And it takes like 800 manufacturing steps to make like a Pentium processor now. The manufacturing process is very complicated. So again, it was a prediction. So Gordon Moore what he did is he observed what was happening in 1959 to 1965, and he plotted his progress on semi-log paper, and he said, wow, look at this. He made a prediction. He said that our complexity doubles yearly. So chips become twice as complex, twice as capable, twice as small, whatever you want to use as a yardstick there. Costs less to produce them. And he made this observation that if we keep doing this in the next 10 years, we'll double our performance, we'll have our manufacturing costs, and we'll do this every 18 to 24 months, because that's what we've done from 1959 when I was at 764 microns in size of features down to 1975 when I was probably down around 40. Now to go from 765 to 40 in 15 or 10 or 15 years is challenging, but it's nowhere as near as challenging as going from 32 nanometers to 22 nanometers. So think of the economy of scale there. So we've taken this idea of shrinking devices and all of these challenges is wrapped up in this kind of collaborative document called the ITRS, or the International Technology Roadmap for Semiconductors. If you go on the Semitech website, you can find a link to this. And it's hundreds of pages of the challenges that face not only photolithography, but the RF guys, the etch guys, the material suppliers. So all these guys have these targets that try to get them to narrow down and make things faster, smaller, cheaper. So it's an interesting document. If you're having trouble sleeping at night, highly recommend it. All right. And I always call Moore's Law the exception to Murphy's Law. 800 manufacturing steps, 22 nanometers. I'm still amazed that we can actually make these things work. And I've been working in this area for over 30 years. And it still amazes me that this stuff actually works. So what does this mean to you? 1978, when I first started at IBM, I bought a programmable calculator for $600. Big thing. Wait, I wouldn't want to drop it on your toe unless you were wearing steel-toe boots. 2013, if you go down to the Walmart, you can spend $10 and get a programmable calculator that's more powerful. Is it on? Oh. Test? Test? Oh, there we go. Everybody hear me all right anyway? All right, I'm going to start over. All right, so again, a calculator, $10. Who's got an iPhone? All right, do you ever use your calculator on your iPhone? Do you ever turn it sideways? You get a scientific calculator. It's an application on your phone. It's more powerful than that thing I spent $600 for in 1978. That's Moore's Law. The circuitry that's inside that calculator, the circuitry that's inside that phone, represents what Moore's Law has done. 10 years ago, I actually bought this computer, paid $2,400 for it. It was a 1 gigahertz processor. It had a 256 mega memory. It had a 30 gigabyte hard drive. Woo! $2,400. And I had to buy the monitor separate. It was another $400 for a 19-inch monitor. Anybody seen what you can buy for $900 in a desktop computer these days? You get terabyte hard drive. You probably get 2 terabyte now. 21-inch monitor included. You can't even spend $1,000 on that computer. That's Moore's Law. It's that economy. It's that efficiency of bigger wafers and smaller lithography and smaller chip size, more economical manufacturing. That's what's resulted in your daily life. This 3D TV, 16:9 aspect ratio, 1080p high definition, 600 microsecond refresh rate, $900. That TV was $15,000 10 years ago. Next year it'll be probably $700. So I'm waiting. I'm still waiting. I'm going to wait till they give them. I'm waiting till they give them away for free. And again, in 2013, this is why R&D consortiums are willing to spend billions of dollars. Manufacturing facilities are willing to spend billions of dollars to put in these 300 millimeter and 450 millimeter manufacturing facilities and R&D facilities. This is, again, Moore's Law. It's all reflected in this slide. All right, so now we're gonna go into some other topics here. Smaller chips. How do we do smaller chips? Where's your BIV? Where's your BIV? Okay. Where's your BIV? You already seen this. What is it? Okay, the rainbow. It's the colors of the rainbow. You know, a photolithographer would tell you it's the visible portion of the electromagnetic spectrum. You know, we call it light, white light. Well, I'm going to show you a couple formulas. All right, what's C equals lambda F? Speed of light. Speed of light is a constant. It's always 3 times 10 to the 8 meters per second. You have two components. You have a lambda, or a wavelength. You have an F, or a frequency. The combination of lambda and frequency always equals a constant. And the reason I just bring that up real quick is that, you know, light is comprised, and the electromagnetic spectrum is comprised of many different frequencies. But the wavelengths change, it all travels at the same speed. Okay, everybody accept that? I've got a derivation in the backup material if we have to go there. But again, lambda times the frequency equals the speed of light. So photolithographers have used these shorter and shorter wavelengths of light to shrink circuits and chip sizes. So again, this is one of the bigger knobs that we have to enable us to get smaller and smaller chip sizes. So here's just a kind of a reference scale here about wavelength and frequency and the relative size. You know, the part of the electromagnetic spectrum that we're working in lithography is in the the red, the white light, down to the ultraviolet, down even almost to X-ray. So this is kind of the useful wavelengths to photolithographers. And here's just a good representation. You know, I put this on there. You know, if you don't plot it the right way, you end up with VibGyor. Man, tough crowd. Yeah. But anyways, here's RGBIV. And again, the wavelength, the frequency, the frequencies we're using are visible towards the ultraviolet. So this is the band of the electromagnetic spectrum that photolithography uses. And again, Warren has a little bit more on wavelength and frequency and a little bit later in his part of the presentation. Again, trade-offs. Just real quick, couple more formulas, and then I'm done with the formulas. Of course, Warren will have a few more. But speed of light is a constant. It's a product of the frequency and the wavelength. And then if this is our derivations of what's called the Rayleigh equation. And but all you really need to know is that, its position in the equation is that this is in the numerator. So if shorter wavelengths, if this is a bigger number, the CD it's able to resolve is going to be a bigger number. If it's a smaller number, the CD that it can resolve, the critical dimension or the feature size, is smaller. So again, its position in the numerator is just going to be big. Bigger's bigger, smaller's smaller. That's all you really need to know about this part of the equation. The trade-off is, however, my depth of focus. This kind of, everybody kind of comprehends depth of focus when you have a camera. If you have a certain f-stop on your camera and you take a picture, and the face is clear but the background is blurry. Well, imagine that down on the nanometer scale, and you have the same. Things are in and out of focus in a relatively small dimension. The depth of focus then is proportional to the wavelength. If I'm using a shorter wavelength, I have a shorter depth of focus, all other things being equal. So it's a good thing to be able to use smaller wavelengths to resolve smaller and smaller feature size. However, there is a trade-off in depth of focus, and that's you start spending a lot of money to get better depth of focus control in a modern photolithography stepper or scanner. Okay, so through the ages, this is kind of the wavelengths of light that have been used in photolithography, shrinking. We've gone from broadband white light to more narrowband laser-based exposure systems. So the old days, back in the 60s, actually Warren and I were talking about this, that, just like you can use wafer size to kind of estimate, if somebody said to me, okay, or if I asked you, okay, what wafer size were you working on when you first came into the semiconductor industry? If you said 1-inch wafers, you're like 55 years old, okay? If you said 200 millimeters, you probably came in the 80s. 90s for 300 millimeter. If you said 450 millimeter wafers, I'd say you might be a technician at Hudson Valley Community College, because it's really not in manufacturing yet. Same thing with wavelength of light. What light did you use? What wavelengths did you use to pattern the most stringent or most complicated device component? And I could tell you that if it was white light and you were using broadband illumination, you probably were in the 70s. G-line, H-line, I-line UV, using a mercury vapor lamp as the light source, probably early 80s. Deep UV came about in the late 80s, early 90s. And then we've gone from mercury vapor lamps with filters down to, and the reason we made this change is the same wavelength of light using a mercury vapor lamp, but we went to this excimer laser because of the cost of ownership. You can imagine these mercury vapor lamps were this big. They used an incredible amount of electricity. They lasted about 250 hours, which means you have to change them every 2 weeks. They were like $5,000 each. And then you got a lamp that's got like half an ounce of mercury in it. And hopefully everybody realizes you can't just throw that in the trash. I hope you realize that. Same thing with your batteries, please. Recycle your batteries. So there was this device in the early 80s. Anybody know what an excimer laser is? So an excimer, who's familiar with Star Wars? I am not talking Obi-Wan Kenobi Star Wars. I'm talking about the real scary stuff, the Space Defense Initiative. Remember back in the late 70s, early 80s, there was this plan to put these chemical lasers up on satellites, and when the Ruskies launched, we were going to blow them out of the sky with these chemical lasers. Well, that never really happened. But the offshoot was that type of laser is what we actually use in our lithography tools these days. So your tax dollars did not go to waste. Actually, were quite useful, and it kind of enabled a whole nother level of manufacturing in photolithography using excimer lasers. So, and then Warren's going to talk a lot more about these individual steps, right down to extreme ultraviolet or 13.5 nanometer light. We did have a little kind of a setback in the mid-90s. We actually explored these 157 nanometer excimers and exposure systems, but we found out that the light energy was so energetic we couldn't find materials that could actually stand up. Lenses became consumable items. After about a week, you had to change the lens at $1 million because the materials, quartz would crack in the presence of this exposure. The quartz is typical lens material. They tried calcium fluoride, cracked, compressed, couldn't use it anymore. So 157 went extinct. And then again, you can kind of see here the year and what wavelengths were we using and when are we projected to be in manufacturing for EUV. Again, this is that shrinking of dimensions enabled by smaller and smaller frequencies. Excuse me, smaller and smaller wavelengths for exposure systems. All right, so now I'm going to turn it over to Warren Montgomery. Warren's going to talk about the photolithography process. And, thank you. Right on the podium.
Okay.
See, red button gets you the
advances.
Let me turn this off in case I start snoring.
Thank you.
I think that could possibly happen.
Okay, I need a minute here. Okay, good. All right, so first of all, I want to say happy to be here with you today, talk to you a little bit about photolithography. I would just say I'd add one point to some of the things that Andy was saying, and that is he talked about smaller and smaller chips and so on, but why do we care? Right? Why do we care that you put a whole bunch of chips on this wafer? Well, what we're taking advantage of is what they call economies of scale, and you've probably heard that if you've taken economics or anything like that. What we're trying to do is take a given process step and get more out of it. So if we can, we started out with these smaller wafers, and we were imaging those, and at the time, we yielded X amount of wafers, and that allowed you to have, for example, calculators and maybe certain applications for your games and so on. By shrinking these chips, we make these chips faster and also enable your phone and so on to do more things. So the reason why you have that iPod is because we're able to cram more information into those chips by making them smaller and faster. And that's the drive. So the pull for all this activity is right now your games and your ability to use your cell phones to do all these things that you love to do with them. So that's really what's driving this, and it probably helps think about that. It helps us understand why we're doing that. The companies that are working at Semitech and working at the College of Nanoscale Science, they're not doing that because they're generous companies. They're doing that because they're making money. And the reason why they all work together like that is because, as Andy mentioned, these tools are getting more and more expensive. That wafer, and what he didn't tell you about, is if you were to go out now and buy these wafers, this wafer here, for example, you could probably get one of these, I'm thinking $80, right? I know right now that we get these for $200. This baby, $7,000, okay? Heavy, yeah, but limited supply because we're just now getting in that technology. So as you scale up the amount of materials you're in, the price goes down. So right now, it's very expensive for a company like IBM or Intel to work with this kind of wafer. It's cheaper for them if they pool their money. So now IBM pools their money with Intel, with AMD, or what was AMD, now it's Global Foundries up the street here, where you have an opportunity to work one of these days. They pool their money, and so now that $150 million system, if 6 big companies put their money into working on that one system, it doesn't cost them $150 million. They pay a portion of that. So I'll talk a little bit more about that, but I thought it was probably important for you to understand the real driver. So let's talk a little bit about litho. So photolithography, it's the march to printing smaller dimensions and faster devices, which I just mentioned. What we're really going after is leveraging the scanner and stepper. These are exposure tools that define the pattern on these wafers. The materials, the photoresist. And then, you know, there's some games that we play because as we start printing smaller features, they don't behave the same way they did when we were printing the larger ones. And, you know, one thing I'd like to tell you is when we started, and he was talking about the first wafer you started with, I started with a bunch of different kinds. Actually, there were 2-inch wafers. He doesn't have them shown here. But 6-inch 2 was what we were using in production, 6-inch wafers. And the patterns that we printed then, we are trying to print something smaller than the bias of the pattern. So he talked about a 10 micron pattern. When we were printing 10 micron patterns, we were happy to print a 10 micron pattern with a bias of 1 micron. Now we're printing nanometers, like 20 nanometers, which is, you know, 10 times smaller than that, right? And it's interesting for me to think about this because back when I started, I was working in materials, as he said. And it was interesting that I remember when we went from 1 micron patterns down to half micron, I thought to myself, there's no way we're ever going to be able to print that. And then we were. Now we're way smaller than that, you know, 10 years later. So you wonder, when is it going to stop? Andy talked about the $150 million tool. That would be the EUV tool that I'm going to talk a little bit more about. This thing, okay, there we go. This EUV tool. Okay. All right, so we talked a little bit more about this, and it helps to really see. When we talk about lithography and photoresist, this is photoresist, okay? And this is photoresist on a wafer. And here we're depicting a mask. So the mask is what defines what the pattern is going to look like that makes the chip. So it's very important. This is the silicon wafer, and you notice that we're shining the light through here. It's going through this lens looking material here, and then it goes onto the mask to print this pattern. I don't like this, but it's probably accurate, right? It goes through a condensing lens. I'll show you a little bit more about that later. So this pattern is printed on this to yield these things that you all know and love. We'll talk a little bit more about how we do that down the road here. Okay, so as Andy mentioned, the goal, print more and more of these guys, smaller and smaller, so that we can do things like put them in cell phones. And the other thing that's happening is not just shrink them smaller, you know, like urban development. If you live in the projects, right? I'm from the projects back in the day. But anyway, what happened was when we started getting a lot of people living close together, what did you do? Did you have one bedroom, you know, one family, one-story homes? No. You went to the tenements, man. They went several stories up. You started building up. So we're doing that right now, and you'll hear people talking about this. They call it 3D integration. So they're starting to take advantage of building up. Because if you open your phone has a lot of space in there up. And the nice thing about building up is all this old technology becomes new again. It's a different kind of difficult. And actually, Andy is from that era. Maybe he'll do a little discussion about that for you down the road. So I won't talk about that too much. But I'm just saying that there's tremendous opportunity for growth and continued advancement in this technology. So I think you've chosen well. Okay, so we talk about the silicon wafer. How do we get these silicon wafers? Well, we grow them, right? What we do is we have this, oh, I'm sorry, still got to figure this out. We grow the seed, right? We have this string that acts to attract silicon molecules. And then we grow this ingot. And then once we grow this ingot, which you can see here standing next to this young lady, rather large, right? See, it comes to a point. We saw it. And Andy's really doing a lot of the work with this. I haven't worked in this area. I'm just familiar of how it happens. But Andy has actually seen these saws and is familiar with we got to polish these things very flat. You see how shiny they are. They're very polished. It's very important that they're flat because any kind of bumps and so on causes problems with our lithography process, which I'll talk a little bit more about. But you can see that, you know, from that silicon chip, you go from that silicon wafer, you got a mask here, you got wafers. We go to many applications in our lives that we've come to know and love. Okay, so in a fab is really constructed of a number of areas. One we call thin films. In lithography, what we really do is we treat an area, for example, with a metal. And then we want to take the metal out of certain areas and leave it in other areas to make the circuits. That's what carries the information. So the way we do that is we do this masking process with the photoresist. That's what defines the patterns. So we'll use these thin films, for example, oxides or metals. Here's a polish step because we need them very flat, right? And then you have litho in the middle. And he said litho was the most important thing. I love to think it is too because I spent most of my life in it. But it is. It really is because there's litho steps that define pretty much everything, right? It defines the patterns that we're going to use to diffuse mobile ions, which carry the current. It also defines where we're going to etch patterns when we're going to make metal lines. How do we do that? The photoresist defines that. We're going to implant. We put those active ions in a certain area. That's here. Diffusion makes them move around where we want them. Implant places them. I'll show a picture of that later on. And you know, you can see this is the basic functioning of the fab. It looks very simplistic. You know, you make those layers, you build that chip up, then you got to break it into parts. This is the wafer. We send it to test to make sure it works right. And then we break it into the many parts. There's several pieces that go on your phone. And that's why having the bigger chip makes it very cost effective. Because if we are able to take in one step, and for example, litho, we can expose many more chips in one particular process step using that one engineer, technician, et cetera, and then break it into parts. That lowers our cost of manufacturing. It makes it very affordable. So that's what's driving the larger wafer, right? Because at one point, it used to be very affordable to make chips. You guys are entering the era of the single wafer process. But when I started, when Andy started, we used to do batch. And what batch means is we had boats. Remember this? We had boats of wafers, 25 wafers, and we would have big tanks. And one technician could be in the center. And if you can imagine, you had your exposure tool here, you put your wafers in, they expose the 25 wafers. When the 25 wafers were done, now you have to develop them. So you turn over here and there's a develop module. You take them, you stick them in. This one person could do all this, right? Once they come out of develop, they might have to go to a bake or a dry step. But you can think about it. All this stuff was around, and it was batch. You did 25 at a time. But the problem with that was, if you can imagine, you got wafer here, and wafer in the middle. As we went to smaller patterns, the wafer in the middle, after we got done with this batch processing, looked way different than the wafer at the end and then the wafer at the beginning. That's a problem. We're making widgets, they got to look the same every time, right? So it became cost effective to make one wafer at a time because we could make them all the same or very close to the same. Now you can imagine, first I was doing 25, now I'm going to 1. How can that be more affordable? But if the first wafer you process looks different than the last wafer, it doesn't really accomplish the goal, so it's a problem. So we moved to the single wafer application. And you know, Andy and I also had the opportunity to participate in a little bit of history, because when we went to the single wafer, it was also about the time that the wavelengths changed to chemically amplified material. And I don't know if he remembers, I remember the first presentation I went to in, I think it was in San Diego, where they talked about the integrated photocluster. And what that means is, before, the scanner, the exposure tool, used to be separate from the coater. So I'd go over here and coat my wafers. Many times I'd walk way down the hall, right, to do my imaging. Then I could take my boat of wafers and go over to the develop module. They didn't all have to be together, right? But at one point, now that we've controlled everything so tightly, you needed to really develop within minutes after you expose, because the whole process was so sensitive to time changes. So we went to a cluster. And I don't have any pictures of that, but it's a pretty amazing thing. If you had the opportunity to see when the president came, you saw a part of a cluster. But what we do now is we have the coater, which applies the photoresist, connected to the exposure tool. So they're all one big unit. And the develop module is in there. So most of the processing for litho is done in a module, self-contained module. The wafer goes in, it comes out when it's done. It wasn't like that before. So that was a pretty good innovation. As I remember, that was one of Andy's earlier jobs, coming up with those integrated photoclusters. Kind of a big accomplishment to where we are now. And IBM was one of the innovators of that. Okay, so I talked a little bit about what happens in the lithographic area. So here's another example of that. When we apply photoresist, that's exactly what it looks like, what you see right there. Now, this picture could be showing either resist apply or developer. That's what it looks like in the coater right now. This arm moves over, drops chemical onto the wafer. We spin it, okay? So let's think about that chemical that we drop on here for a minute, because if you think about your current life, you're interacting with something very similar. And I would put that, I would say that's paint. When you paint a wall. When you paint, paint is made up of a polymer, it has a solvent, and it has a pigment, which makes it have the color. And you roll that on the wall, and you roll it very thin, and you wait for it to dry, and when it dries, it has a certain flatness and texture that you want. Photoresist is very similar. Photoresist has a polymer, has a solvent, okay, and it also has an active agent, which is, in this case, light sensitive. So when we expose it to light, like photographic paper, it undergoes a change where the light has happened, where the light has exposed it. And what's important about the fact that of those components, it's very important what solvent you pick when you mix the photoresist in. First of all, it has to make the photoresist, all the components have to dissolve in it. If they didn't, you'd have particles and junk all over the wafer. You don't want that. I heard your professor earlier say that you guys, some of you have done some experiments where you've applied photoresist and you've spun it and you get different colors. You're supposed to get that. Those are called Newton waves. Those are drying. And when you fully dry it, what you'll see is, first you see those waves and then it'll go to a flat, usually purple color. That means it's all dry at the same rate. We're very careful about the solvents that we pick. They have to have a certain boiling point so that they dry during the spin process. In most cases, it's 140 degrees C. That's the magic boiling point that we pick for solvents. And typical solvents, xylene, which I'll talk about earlier, PGMEA, those are ones that are used because of their great coating properties and their ability to solubilize the materials that we need to solubilize. So in a typical process, we have an apply, which is what's happening here. Then we do a bake, right? So when we spin it, the spinning is to drive off solvent and make the material flatten. And then we do a bake to dry it. So if you painted your wall, the act of you putting it on is the apply. Then you leave it, that's the dry. But in some cases, you may go to a place where they bake it. That's the process we're doing right here. We do a pre-bake. It's a pre-bake because we don't want to harden it so that it's not active anymore. It's just enough to drive probably, when you spin it, you probably get down to 10% solvent remaining in the film. But we want to take it down to probably 5%. So we do a soft bake, we call it. And that soft bake is the step that's depicted here. Then we do a masking step. So this is when we expose through the mask the pattern on this substrate that we want to print. That's the masking step. Then once we have exposed it, there's usually another bake now that makes the chemistry happen. And after we do that next bake, we do a develop step. And that's where we differentiate, okay, here's where I've exposed, I want to clean that out, and the stuff I didn't expose, I want to leave that, or vice versa, depending on the tone of the photoresist, which I'll also talk about a little later. And then, actually, these are out of sequence. This should be a post-bake and then develop. And then we do an inspect and measure of the actual pattern that we printed, right? Because we're not just printing arbitrary patterns. We want the patterns to be a certain size, and they've got to be very close to that size. We don't want them to vary too much, because we're printing widgets, and they've got to be the same. And you guys, for some strange reason, if I give you an iPhone, and it's not quite able to dial the way you want it to, you won't buy it. So it's very important that that phone behave as you expect it. And you don't care where you buy it. If you buy it from Walmart, if you buy it from anywhere, you want that phone to act the same. And the way we're able to do that is by locking in these processes and making them reproducible. So the other thing I would point to is that 50% of the time that the wafer is in the fab, it's in photo. And most of the steps and processes that are done in the fab require litho to define the pattern, which is transferred through the process. So again, very important step. So this is a little daunting. I remember when I first looked at this, I thought, what the devil am I looking at here? But when we talk about implant, when we implant ions, that would be this N area, okay? And this gray portion here is wafer. So the reason why we use silicon is uniquely suited for us to be able to do this kind of implantation, to put impurities into it that we can now turn into what this is, which is a MOSFET. And what it is actually a device. And the whole objective of these things is to turn on and off like a switch. So we put millions of these switches in there to carry information. And if you look at this, here's the gate, right? You have a source and you have a drain. And what happens here is this X area, when we put enough power into this thing, we are able to allow these ions to move across this area. And when we don't put any power in, it shuts off. So now you have a switch that goes on and comes off. And so how do you make this? Well, you make this by, first, you need something to allow you to only pattern this region with ions. Guess what you use for that? Photoresist. I put a mound of photoresist over here, like that. And you can imagine maybe this is where the ions are coming down, and they only go in this area, which is here, right, to implant in that area, and they're blocked here by the photoresist. Then I strip this photoresist, and so any of the ions that got embedded in here, they're gone, because I strip them out. So now the ions are only in that area I wanted them to be. I use the same approach for this, to create this oxide layer, right? I put photoresist here, I put photoresist here, it's got oxide all the way across. Or actually I put photoresist here, like the gate, and I leave that open, and I etch that, and then I'm left with this little area, which is an insulator. It keeps the ions from, it keeps this metal from talking to these ions, because if it didn't, the ions would go up here. It's also conductive. So you want an insulator to insulate it away from the crosstalk, we call it. Okay? So lithography, defining this pattern, defining the oxide insulator, defining this, even this metal. And I'll show you how we do that a little later too. Okay, so this is an example of a simple device, right? When you look, if you looked in your chip, it would look something like this. all these different layers are overlapping. You have contacts doing their job. You have metal lines, right? And you look at that, and it looks very complicated. So let's break it down into the steps. Here, this is a layer we call isolation. So it would be an oxide. So in that deposition, we deposit some silicon oxide or some sort of oxide, and that makes up the first part. Then, I'm sorry, this is the implant, rather. This is the first implant. Then we put this oxide over to protect it. Remember, the oxide was the protecting layer under the gate. That would be this layer. Then this would be metal, right, that would go over the top because I want to have some communication going from that layer to this layer, but this insulator, wherever it is, there's no communication because it stops that. And then I have these contacts that allow me to go from one layer to another. It goes, actually it penetrates all these films, and it allows me to contract multi-layers, right? So when these guys were building these 3D devices, they were working on these contacts being able to communicate way down very large areas. We do the same thing for the smaller chips, maybe 20, maybe 36 layers. But in order for these things to talk to, for layer to layer to talk, you need these to go through. There's an insulator around them so that only where this connects to the next metal layer do we get communication between the layers. So this is a simple example of what's going on inside of an exposure system. And notice that equation that Andy was talking about, and I'm really kind of highlighting the knobs, right? One knob, we reduce this K factor. K factor is what we call our process constant, right? Depending on how complex the processes that we're using, there's a constant that has to be taken into account, and that's that. Andy talked about the wavelength. What we're doing now is reducing it because we want to make this whole equation small, and thus we get a smaller feature size that we print. And then NA, right? So you make the top bigger, right? That helps. You reduce the top, that helps you. You make the bottom bigger, so you're dividing by something bigger. That also makes this equation smaller. That helps you get in your line width. So there's a number of approaches we can use to get there. One, we can do something to the light that's coming in. The next thing, we do something to the photoresist, and actually you kind of those have to work in concert. The light that you're exposing with has to be sensitive to the new light or the new wavelength that you're using. So that's a very important connection. The mask is a very important part of that. And you notice the stage. The stage, very accurate. It allows you to print those little chips. Can you imagine those little small exposures that you're doing? That stage has to have amazing control to be able to print that very small feature reproducibly. And at this point, typical scanner is putting out 125 to 150 wafers an hour. So hundreds, thousands of chips, hundreds of them an hour, 125, 150 an hour. Very impressive technology in the way of the scanner. So with that, segue into the exposure tool. And there's that equation again. We're not going to be intimidated by it because we know it's a pretty simple equation. I keep showing it to you because I want it to become part of your thought process. It's the driving force. So when I talk about the scanner, the area we're going to focus on is the reducing the wavelength and the increasing the numerical aperture. Kind of a complicated slide, a little busy. I'm going to walk through it slowly, just for information, right? I don't expect we're going to test on this, but it might help you later on down the road. So when we started out, Andy talked about this, we did contact printing. I mentioned earlier, actually when I started, in some of my early papers and things that I think about, I was happy to get 10 micron patterns, 10 micron. And we used contact printers. The mask was actually in contact with the wafer to make the pattern. So you think about that for a minute and you think, okay, if I had paint and I put it on the wall and I baked it, hopefully I've driven off all the sticky stuff, or when I put my mask on it, I'm going to get sticky stuff on my mask. Well, sometimes we got sticky stuff on our mask, so we had to get away from that. And so that was one of the driving forces that moved us into this, what we call proximity printing, where you print close, but you don't let the mask contact because you don't want that junk on your mask. So let me think about this for a minute. If I get junk on my mask, which is my stencil, that I'm going to make multiple chips on, What happens to my multiple chip? Maybe chip 1 looks great, but now I got junk on the mask and I'm shining light through, and that photoresist stuff blocks the light. And so now I go to do the next chips. What do I have? I have defects on my wafer. Wherever that junk is, it's not printing. And when it shows up on the chip, that chip isn't looking like it's supposed to look. And when you buy your phone, it's not working like it's supposed to work because there were some lines that didn't print and stuff that got blocked, right? So that's a problem. So we went to this proximity printing to have a little bit of a space here. But when there's space, one good thing about contact printing is here's the pattern, here's the wafer. The information is getting transferred pretty quick. The only problem I had was the thickness of the glass, not much, especially when you're printing a large line. When you went proximity, now you're adding error, right? Because now you have that space, you have information being lost as it goes through that space, all sorts of diffraction and so on taking place. So it works against you, but again, when we were printing large patterns, we could deal with it because the amount of error that we could tolerate was relatively higher. So now we've moved to this projection printing. And what's interesting about this, and you see these complicated lenses now that we're projecting the light through. The light comes down, and when it starts out, it's actually 4 times bigger than it is when it hits the wafer. That helps us, because if we make mistakes up here, they get divided into smaller chunks. So at the wafer, they translate into less error. So that's a benefit. However, we still got this space thing, and a lot of bad stuff can happen in that space. So we'll talk a little bit more of that. A little bit more about that. So I talked about this, if you can imagine, this is the light coming in. You have this mask, right? And light is viewed as a point source. So that's the reason for these diffusion waves, but you don't need to worry about that too much. The key is we image that photoresist there, define that pattern on this wafer. The resist blocks the light. And depending on the type of light you used, you can see the waveform that's formed from the light. And in the case of projection printing, we're actually operating with this Gaussian curve, which looks like a normal distribution, right? Many of you probably have already talked about that. When we used to get from other printing, from proximity, we would get this wave. But it turns out that we can do some wonderful things with this much information. It's enough information to get very good or usable imaging later on. So inside a scanner, the scanners that we're using today, this is sort of the way they look. And what's happening right now is sort of a revolution, right? Actually, I wouldn't say right now. It happened a number of years ago. I have a slide that talks about exactly when these tools were introduced. But one of the big things that happened was this transition from what we call dry systems to the immersion system. But I'll talk about that in a few minutes. A typical scanner, I mentioned before, there's a track that goes here that coats the photoresist on, right? Then it feeds this wafer into this tool, goes through the exposure process, goes back to the track, and gets developed. So it comes in, it sees the light. The light takes a very interesting path here, very complicated. It gets even more complicated as we go to EUV. But the other thing to note here is, this is transmissive. So the light is getting transmitted through, right? We'll make a distinction about that when we do EUV. We're going to go to a different system. This whole thing will be under vacuum, and all the optics are reflective instead of transmissive. So they're all mirrors. That's an interesting new challenge, and it's something that's causing us a lot of headaches, but a lot of good job opportunity for me into the future. So anyway, let's talk about this here. Back when we started, for the most part, all the tools were dry. So we were doing contact printing. You put the mask on top. You put the wafer here. We had a box. It did flood light. Andy called it broadband flood exposure. It didn't differentiate the wavelength. You saw a wide range of wavelengths that were exposed. We didn't really care that much because we weren't so sensitive because of the tolerances. But as we became more sensitive to tolerances, we had to filter those stray wavelengths down to specific ones. 248, 365, 405, 435. And so the systems became quite complicated. There's a number of filters in here. All these optical systems are geared to really streamline the kind of light that the wafer actually sees, because we wanted a certain property in that light that the photoresist was going to see. So the transition was just change the wavelength by changing the laser that Andy talked about to a different wavelength laser. So he showed a table that talked about the excimer, 248 laser, 365, 405, right? And I have some plots that show that a little bit better. But those were all dry systems. What we mean is, here's the ocular, here's the wafer, there's an air pocket in here. So if you think back on your microscope, right? You've probably looked at microscopes, right? Folks, microscopes? You ever notice that there's that one ocular that when you try to pull it down, it gets so close. A couple times I've messed up and actually hit the stage with that thing. That's not good. But anyway, the reason why you have that last one is really not so you can look at it, look through that. The point of that is so that you could put an oil in there, and then you have immersion. Well, that's what we're doing here with the big systems. We're doing immersion. And in this case, the liquid that we're putting in here is water. What you really want is you would like to have fluid in there that had an index that was similar to the index of your optics. Because if you had that, then what you have is a continuous lens, right? In this case, you have this space in here. You get all sorts of changes in the way that the image is projected on the wafer just because of what we call the index of refraction. But if you didn't have that dramatic change in index of refraction, more of the information that you're sending through that optic could be communicated down to the image that you want to print. It would look more like what you want to show. And so we get close to that with water. Water is actually not the most ideal material for that. But water does work well on top of the photoresist, because most of the materials that would work well in this application are hard to handle. They're hard to get rid of, and they actually start attacking the photoresist, and then we don't get the benefit that we want to get. So water, the resist is waterproof, and that allows us to get away with using water. And so by doing this, we get a much greater depth of focus. And I'll talk about why depth of focus is important right now. So here's depth of focus, right? What I'm trying to show here is, I said that with photoresist we can do a lot of things. We can print things and so on. So somewhere in the process we printed this metal line, okay? And now maybe the next step is we want to print a via. And the via would be, we would cut an opening here and maybe deposit some more metal and then put another metal line up here so these two metal layers can talk to each other. So what we would do is we would do our lithography to yield this metal line. We'd coat photoresist on the top, right, because we're going to mask it again to do something. All right, so here we talk about depth of focus. When you have a large NA, as Andy talked about earlier, all of a sudden you have a smaller distance that you can work on. And what that means is when you're printing, if you have any kind of a change in surface like this, you get a change in performance of the photoresist, which I'm showing here. So what these are is we tried to print a number of different size lines, which is what these are, photoresist lines, over changing focus and changing size of the line that we're trying to print. And what you can see is we get this, what we call spider plot. And what that shows is if I'm printing a 25 nanometer, or let's say 30 nanometer line here, that's the blue line, as I change my focus, my feature starts changing. And that's why this blue line does a little drop there. There's no data there. That's kind of a terrible extrapolation. But in any case, that's kind of what happens. The CD changes as I change my focus and my exposure energy. This is called the focus exposure matrix. We do that because we want to find what we call the isofocal point. The isofocal point would be this flat line. Because what we want is we want to be able to expose any layer and not have to worry about focus. So we want the isofocal point. Now the problems that we encounter are, and you can see this is ideal. But what if, when I bring my wafer in, I get some junk on the back? We call it hot spots, but some foreign material. It goes in a resist coater, right? What if some photoresist gets on the back and it sticks back there? And now all of a sudden my wafer isn't really flat. It looks flat because that particle is small, but when we're printing such small features, when we're printing such small features, it's not flat anymore. So if I have a larger depth of focus, it allows me to ignore some of the stuff that's going on, non-uniformity in the resist, for example. The fact that this has this hump in it, right? It allows me to be less tolerant, less sensitive to that, because I have the ability to go a little bit in and out of focus without changing my feature size. Now this is a lot to go out of focus, so maybe you would see this change in feature size. You'd have to do something else. But you can see we change the focus. If we're at isofocal, we have pretty good. We can go from 0.1 all the way to, I don't know, 0.25. So a particle that size won't make me not print the size feature. Double negative. If I have a particle like that on the back of the wafer, it doesn't inhibit my ability to print the target feature that I'm trying to print, because I have that nice depth of focus. So this is just to talk to you about the evolution from what we used to do. Is we had a tool called a stepper. And the stepper would go to this spot, expose one chip. Go to the next spot, expose one chip. Go to the next spot, expose one chip. And that worked great for a long time. But there were some problems with it, right? Because it's almost like that batch processing. It was exposing every chip individually. And so we lost our ability to really print fast. And so we started looking, as we do in lithography, we're always looking for a better way of doing the work that we're doing. So the great folks at the scanner companies came up with this idea of a scanner. Scanner has a slit that it scans across. So now we're exposing multiple wafers simultaneously. And then they actually came out with an ability to do two wafers. They call it twin scan. It's got two wafer stages, and it's doing them inside the chamber together. So now the total time it takes to process a wafer can be sped up. And that's why we got up to 125 wafers an hour. When I started out, we were like 80. So that additional stage and the scanning technology allowed us to go to a larger, I keep doing that, a larger field size and higher throughput, increased throughput, but also better CD control and overlay. Overlay is very important. What is overlay? So I talked about how we print one layer and then we want to print another layer on top of each other. If I'm off, then my device isn't doing what it's supposed to do. So my ability to have these overlay each other and match up, very important, right, to a working device. If I do that misprocess, it could pretty much kill all this investment that I put in here. So we want the scanner to very accurately be able to put the pattern down and have it line up with the next pattern below it. So that when we make these integrated chips, thousands of them, they all look the same. So the key takeaway here, scanners deliver better CD control and overlay and increased throughput. In your careers, you won't see the stepper anymore. You'll be working with scanners. Lucky you. Okay, so here I tried to show you a little bit of history of the tool sets. This particular tool set is created by a company called ASML. They happen to be the largest equipment company in the world right now for semiconductors. They just passed, in terms of sales, they just passed Applied Materials because of the $150 million scanners that they came out with. But prior to that, it was Applied Materials. They make a whole suite of different tools. These guys only make this, they specialize in this particular tool. They actually have some mask tools, but the real drivers to this industry is this tool. So what's nice about this plot, if I say so for myself, having made it, we talk about 6-inch wafer, 8-inch wafer, and you can see that when we were doing I-line, and for that matter, G-line, H-line, we were in this area here. And then about 92, we moved over to 8-inch wafers, I-line. Then 96, right, we went to the step and scan. That's this system. A little more complicated than this system. And the other thing that happened was when we went to KRF, which is what this says here, we had to change the resist system. So back here, there's a saying that they say for the mask makers, and that is, they call it mask makers holiday. What the heck does that mean? Well, there was a time when the guys that were making the masks so that we could do the patterning, that's these guys, right? They got to keep the same process, same materials. They had to do very little work in order to enable the lithographic roadmap. So they were on a holiday. They got to take it easy. And I would say the resist guys, we had a holiday too. And our holiday was back in the diazo days. Because we got away with using diazoquinone resist for I-line, G-line, and H-line. They changed all those wavelengths on the scanner, and we didn't have to do any more work on the photoresist to have a material that worked. However, when they went to KRF, we had to come out with a new material. So, resist guys holiday from here to here. Okay, so the next tool from the KRF was the ARF, and that's the 193 systems. So I'll just go by wavelength. This is 405, 435, 365 in here. And then here we went to 248, and then here 193. And then from 193, we went to immersion. So one thing that you can notice is that we had a really long time where we didn't have to change the wavelength too much. And we were able to make use of similar laser optics and so on. Maybe the system changed a little bit from the way that it exposed, the overlay got better and so on, but we could still use the same wavelength. When we went to KRF, that's a whole new system. It was a step and scan. We wanted to get the throughput up, and then the wavelength changed, and the resist system had to change. And this is what brought it, this really ushered in what I was talking about before, the integrated photocluster. It had to all work together. And the reason for that is if you look at this up here, and I'll talk a little bit about it more, this says H+. That's acid. How many of us know about acid-base chemistry? Right? What happens if an acid encounters a base? Neutralized. So, you have a photoresist, that's an acid. You have somebody who ate a tuna fish sandwich, and they're kicking off some amines. What happens to the photoresist if they breathe on it? It don't work. So we had to figure out a way to protect the photoresist, and we came up with all sorts of ways. We would put top coatings on top of the photoresist to protect it. Then we went to integrated clusters that were, we had inert gas pumped in so that if you breathe that stuff, it wouldn't get in there. First of all, you can't get close enough to do it. And that's kind of the way the fab is set up now. Keep the human element out. So Andy was talking about the president coming to visit. What he didn't mention was we walked into the fab, which it was almost like it had a force field on it for me, without our stuff on. We didn't have a clean room suit on. You know, and you guys didn't see this, but about 4 hours before, they were trying to get the engineers to go in there. We wouldn't go in there. It was like a force field. We couldn't get it. We couldn't make ourselves go in there. So they said to us, look, it's okay, go in there. So we went in there, we were very uncomfortable. They had us waiting 3 hours before we came because we were very uncomfortable when it showed. They wanted us to calm down, and it worked. We calmed down. But we're used to having the whole clean room outfit on, but in reality, we've put in so many levels of protection that it's not important anymore. Because the wafers are in what we call these FOUPs, or pods, and they're, I don't know, 10 parts per billion. And the fab has positive pressure pushing air down into the floor, and it's filtered. And so the wafer never sees the outside. So really, those mini pods are enough, and the tools are all self-contained so that you can't, you know, they're very clean and evacuated. We didn't run them. We kept them closed, and what we did was basically purge everything. It took us an hour to purge the place, and we were back down to the same defect level that we started out with. Very little spike. And by the way, what you also didn't hear is that they had a sniffing dog go in there. So there was a dog in the fab, okay? And, you know, it didn't impact us because we have so many... No, we don't have any pictures of that. Somebody, if you took a picture of that, somebody had to kill you. But, you know, we have so many safeguards in the fab now that we're protected from most things. We kind of make them dummy-proof because it costs so much to make these wafers that we just can't afford those kind of problems. Okay, so this is a typical exposure tool, a little more complicated version so that you can see the inner workings. You can see the optic system here. There's a wafer handling stage and so on. Very complicated system. Here's where the user inputs what they want to have pattern. I got a quick story I got to tell you about that. So the president's coming, and I know about it the day before, and I'm thinking, wow, I want to show him this cluster working. So I came in, and I put this awesome pattern on here, printing a wafer, right? And the nice thing about it is this thing shows you every chip on the wafer as you print it. So I had a nice one depicted on here, and I had the wafer going in here, and so he could see all the steps that it went through, because I thought, yeah, he'll be impressed with that. And so I had that up there. Okay, so we go in the fab, and the way the fab works is that area, this area in the fab that we're in is up against the wall. And there's an open space, and then there's another area over here where the surfaces that supply the scanner are. So the chemicals, the gases, and so on are kept over here. And that's pretty wide, and there's some openings in it. So the guy that comes by and he's looking over the place for the president, I said to him, yeah, look at this job I got set up. I'm going to take him down here and walk down. And the Secret Service guy says, he's not going down there. What do you mean? No. You're going to go down here. The back of the tool, right? So I'm looking at this and I'm going, but you can't see anything from the back of the tool. All the action's on the other side. I'm sorry, he's not going over there. My only thought, nobody told me, is because of that hard wall, they always want to be able to have multiple escape routes. So he wasn't going to, he's not going down there. He's going down here because they can always get between the tools. There's other avenues of escape, and that's what those guys were thinking about. So I had to figure out, okay, let's see. If you look real close, there's a spot where you can just see the wafer come through. So if you go to CNSE and you look to have in the rafters some pictures, you'll see me pointing. That's because that's the only place I could point to where he could see a wafer in the back of the tool. So we're looking at the back of the bake tool, right? And I was just, after all that work, I was kind of just disgusted. But anyway, that's the story. So you have a little insider information. So here's a pattern, a typical pattern, and I looked at a lot of these when we were developing Resist. These are nice because we print patterns in X and in Y, and we want them to print the same. It's very important. And then we also will, these are just telling you what the feature sizes is. Now, by today's standard, these are huge features. We print much, another decimal point out compared to these, so these are very huge, order of magnitude. So this is a little bit of what's going on in the optics, and I mentioned this before. You have light coming in, and we have a number of games that we play with illumination. So this is on axis. This is typical with no changes to the optics or anything. This is how we expose a wafer. The light comes in, it goes through this condenser lens, it goes down like this. You see some diffraction going through this lens, and then these are called orders, right? You don't need to own that, but orders basically are, I would just say, vectors of information. We know what vectors are? Okay, vectors of information. And the goal, because they tell the wafer what the original pattern on the mask was that we were trying to print, is to get as much of that information into this point as possible. So with traditional imaging, what happens a number of times is we print, and over here we lose some information off the edge. What we need is at least 2 orders of information. That's 2 of these big waves here to communicate their information down there to get a reasonable pattern. So an approach we can use is what we call off-axis. And you can see we deliberately lose that guy, but we get this wave and this wave down there. That's enough information to make a nice pattern. And what we find is we get very good imaging by giving up this wave and just capturing both of these 2. They're well in the sweet spot of the lens, and we capture all that information. We get very nice imaging. So by using this off-axis approach, we're able to get a much better pattern on the wafer. And that's why who would think about, cocking the light this way and getting a better image? But it works. The other thing we can do is, these are apertures, which I'll talk about a little, maybe here. Yeah. There's a number of other illuminations. So if you think about it, this light that's coming through here, we can put these obscurations in place that also change the kind of light that's coming down on the wafer. And by doing that, in the case of the dipole, it's the same principle, right? Those 2 orders come through there, we get very nice imaging. Quadrupole also gives us very nice imaging. What we have in the center there, they call the fly's eye. It's the center obscuration. Gives us the ability to knock out the 0 order and just pull in minus and plus 1 order. And that gives us good imaging. So all these things are focused on trying to give us the best imaging for certain patterns. And certain patterns benefit from different types of an imaging light that it sees. For example, if I'm going to do a contact hole, contact holes, a lot of photoresist, you're drilling a little hole in it. You need a lot of juice. So typically, we get away with the conventional. We make this thing as small as possible and we shove as much light in it as we can, because what we care about is getting widgets through fast. So And if it's a high dose, that means it's a slow exposure. It's like your camera, right? If you change the shutter speed to the slowest one, it takes a long time to take the picture, and you better not move, so you use a tripod. Same sort of thing here. If I'm doing a contact hole, I don't want to sit there and have the scanner just expose, and now I want to chug. So I crank it up and shove as much light in it as possible and get that contact hole printed. So if I think about, as I mentioned, we use different light to get different features to print. This is an example of what happens when you use these different illumination systems. So for example, the conventional illumination here is shown in red. It's the worst, right? It prints this small features, this small range. What we want is higher and longer. And you see the best one we get here is dipole, and I mentioned that. Catching those two orders gives us really the best. These other ones are okay. And there's certain patterns that you can get away with using these other ones because you get better properties. Maybe the side walls of the resist that you coat are better if you use these other illumination schemes. But you can see that there's definitely some benefit, and I'm telling you that there's some disadvantages to using those illumination schemes too. But just another game that we play in lithography in order to print those small patterns better. So I like this picture because it kind of talks about illumination and overlay through the ages. Right? All right. So here, resolution was greater than 1. Overlay was 250. That's huge. Especially since now, and I think Andy showed this, some of our stuff, and maybe I show this a little later, the advanced tool, the target for the overlay, and that's the ability to line up with that layer below, is 2. Back here it was 250. Wow. Just keeps cranking down, right? You can see that the pattern, the resolution goes down. This is talking about in the 90s, as Andy mentioned, as you go through the ages, if you know basically what wavelength people started at, you can pretty much guess. They tell you, hey, when we started, we were using tool, the past 5500 /200. Then you know, okay. I know that because I worked at ASML back then. That's about 96. I started at ASML when they did the /300. That was the first DPV system. So 96 is about when the DPV system came in. And then I talked about the twin scan where you can do 2 wafers on the stage at the same time. This was really an advancement in throughput. And this is the $150 million tool. Notice this optic here. It's a, transmissive. Light goes through it. Here, this is the EUV tool. It's being bounced around. It's reflected. No transmission. This is a vacuum system. So light travels faster in a vacuum. It's not helping us. The throughput still stinks in that thing. But we'll talk about that later. But notice that we're going to smaller feature size. So let's talk wavelength. 365, right? Probably all the way to here. 365, so you can do 400. And you could get a little lower than 400. You could probably get 300 out of a 365 system. Then we had to go DPV. And DPV pushed you down to, close to 100, right? But you didn't get much of a generation. You got like really 1 generation with DPV. Then we had to go to 193. So we went to 193. And in 193, what happened was we did 193 dry, and then we did 193 wet. So you got a little further in resolution, but you needed 2 systems. Let's think about that for a minute. So back here, this system, I bet, was $10 million. This system, let's see, probably 30 million. This system, 50 million. This system, 150 million. Ouch. That's a UV. Okay, so I have to do a sales pitch for myself because these are my tools. So here's this is the first EUV tool scanner made in the world. And that was paid for with your tax dollars and put in the College of Nanoscale Science. This tool has enabled the new tools coming along, a lot of learning. And that's one of the things that CNSC is about, learning. And this institution, of course, is about learning. So this tool allowed them to learn about lasers, how to make good lasers, This thing does a wafer an hour if you're lucky. It doesn't have enough power to be a manufacturing tool, and that's why it's a learning tool. We call them an alpha tool. We call this an ADT, alpha demo. And that thing can print 25 nanometer lines, which at the time it came out was state of the art. Nothing could print that small. The immersion tools that I was talking to you about, and I was talking about dry systems. So I said 2 dry systems. I lied to you. Really, 3. There's the 1200, printed 80 nanometers. Then they came out with the first immersion, 1700i. We were able to get the 50, but we had to use a lot of special optical elements in there to get there. And then they came out with the 1950. Now the difference between these two, really, overlay and resolution. And then you look at this thing and you say, okay, it says E-beam up there. Electrons. Electrons are really small. If you could print with electrons, you could print some really small stuff. And that's true. And you know, they use E-beam to make masks. But we don't use them to make wafers right now. And there's a whole contingent out there that's trying to get it so that we do use them for that. But the reason why we don't is because the throughput on those E-beam tools, a mask every 20 hours. It takes a day for them to expose a mask. When we're exposing these widgets, I told you, 125 wafers an hour. A wafer a day? I don't think so. Right? How much would that cell phone cost? I don't care how small you can make them. So right now, we're doing everything in our power not to use that tool. That's why we're suffering through EUV. And, you know, I'm hoping that in my career, we'll be successful so that you guys have an opportunity to work on it and keep me living comfortably in my retirement. So here's the roadmap for the EUV tools, the most advanced scanners out there. So this is the ADT that I told you about. And I have to tell you, frankly, the reason why I'm standing here and the reason why I came here is this tool. And I want to take a minute to thank Andy, because Andy is also a reason why I'm standing here. My buddy Andy, who closed the door for me going to Texas, opened the door for me coming here. You know, I was working in Oregon. I was working for Applied Materials at the time, the biggest equipment company in the world at that time, doing mask making masks, mask writers, and I was doing the process work on those. I wanted to come work at Albany Nanotech because, like everybody else in the world, I heard about all the great things going on in New York, and I wanted to be part of it. And I wanted to work on this baby, the only one in the world. If you're a litho guy, you want to work on the most advanced tool. You want to be the first guy on the tool. I want to be the first guy on that tool. But anyway, so when I heard about this tool coming, I wanted to be here. And I was lucky enough, Andy got me out here for an interview with Semitech. Didn't work out, but CNSE picked me up. And then, you know, the rest is history, as they say. But I came out to work on this baby because at the time, this 32 nanometers, nothing was doing that. And I wanted to be involved with the team doing that. And some of the early work we did that, you can Google us. We got a lot of early papers that we like to think, help enable this technology to develop where it is now. And Semitech's definitely been instrumental in that. So right now, what companies like Intel and so on have are this 3100 called the NXE. It's right now, probably right now, the most advanced EUV tool out there. Okay, and that tool is only a throughput of 60 wafers an hour. So I told you, right now, with my 193 tool immersion, I'm getting 125, 150 wafers an hour. This thing costs more money, and it's a dog. Right? Why would I? Right? But the other thing to note here is the overlay. Look at that overlay, 5 nanometers. So the next tools that people are waiting for, and we're getting one, that $150 million tool, that's one of these, 3300B. We're putting that over in X, NanoFab X. That's going to be one of these guys. So let me just give you a little perspective. This guy, $65 million, 54 tons is how much it weighs. 54 tons. This guy, I'm thinking 80 tons, right? There's a crane on this thing just to take the top off, 5 tons. The crane over here, 25 tons. These things are monsters. That building is like it is for a reason. This thing, to keep this thing powered, $10,000 a month. Just for power. Okay? I have no idea. This is probably what it takes to keep the city of Albany going. Okay? for power. So,
Your lights are dimming.
yeah.
The alarm's busy.
When you see these brown outlets, don't worry about it. We'll be done with that wafer in a little while. Okay, so we talked about EUV and why right now it's not mainstream. And that's throughput is one thing. But you know, we did a couple things. Immersion, we went from air to water. And you know, we had these big symposiums. Oh, how are we going to do it? We've never had the water on the lens before. Will junk come off the resist and get on the lens and cause us all these problems? Will the pH of the water attack the lens? We paid $1 million for this lens. We don't need that. Will it leave junk on the wafer after we're done and create defects and stuff like that on the next wafer after it goes through the processing? We went through all that stuff, and guess what? We resolved all those problems at work. Wonderful. So now we have this wonderful immersion tool, kicking out 125 wafers an hour, okay, and able to do some nice processing. So in lithography, what we do is we try to make every tool that we have last a long time, because we don't want to go to a new tool. So we come up with all these great processes that when I started out would have been absurd, right? Double patterning. So in this case, this is called double patterning. And one of the big issues with printing is being able to print. You know, you have to print all sorts of patterns. And sometimes you got to print a pattern. Here's one line, it's 1 micron. You need a space of 1 micron and then another 1 micron line. And you know what? I want those lines to be exactly 1 micron, and I want them to be square, not round like a little hump. I want them to be slab technology, okay? So that's hard. We're pushing the optics to extremes. So we learn how to play little games. What is difficult is one-to-one printing. If I want to print 1 to 2, so I have 2 microns in the middle, that's kind of easy. 1 to 5, where it's like an isolated line, that's falling off a log. So I need to fool the process into thinking, hey, you're printing 1 to 2 or 1 to 3 so that I can print those one-to-one imaging, double patterning, right? So we have all sorts of approaches to get there, and they're painful, right? One, this would be the ideal where you expose here, you expose some other space, and you can clean it out. This would be the ideal. But you know, the problem with the frickin' photoresist is it has a memory. It knows that I exposed it once already and hit it with developer, and it wants to change. It wants to behave different the next time I hit it with the developer and the exposure tool. So that doesn't work, right? Because it's not reproducible. So that's a problem. So you have to come up with some very interesting, very difficult chemistry to make this happen. So we take another approach. Another approach is we put these patterns down, then we deposit metal, we strip that metal off the top, and we get these little spacers. We can get rid of the resist, then we get these spacers, very small. We can print these patterns, and all of a sudden, look at that. We can etch those into the substrate, and we have the pattern that we were trying to print in the substrate. And we get some good etch resistance from these things because they're made out of metal or something like that. Hard mask, we call it, very hard material, right? And it gives us what we wanted, the 2 lines close together in the final pattern. So that's one approach. Problem? These are very expensive processes. And there's extra processes. Extra processes mean more money. Every time it goes through a process, costs us money. So then there's this other approach where you have a pattern that you print it, you coat the photoresist on the top, you re-expose now in this area in the middle here, you can make a line there, you develop it, and since that one has been locked chemically, and then you're exposing this one and developing it the first time, it looks like, hey, I'm only seeing the exposure process for the first time, then you transfer that, and you get this funny looking pattern, we can strip that off, and guess what? Boom, we're there again. A lot of ingenuity. And then there's the other one, which is litho-etch, litho-etch. So we make these patterns. These are spaces. We coat photoresist on top. We pattern that photoresist as a positive resist, so where I exposed goes, right? And then I strip off that photoresist, and now I've got my tight. This is very difficult to print. Usually what happens is this little space starts getting chewed up because whenever I print a positive pattern, it wants to be bigger than what I'm printing. It has a positive bias. Or actually, yeah, positive bias, and that's a problem. So the stuff in the middle wants to go. So in order to do this, you have to do multiple etch steps. Big money. The other thing is you need masks, more than 1 mask to do this. When I print straight up, I need 1 mask. When I print like this, I need multiple masks. That's multiple bucks. right? We're all in this for trying to reduce the cost of stuff. So these are expensive processes. But you know, I had a boss when I worked at that last job, and he said a line to me that I always found very wonderful. He used to say to me, I came up with a process to do some work on our first EUV tool with that company. And he said, and I said, well, it's kind of a complicated process, so I got my group trying to simplify it. He said, a solution is better than no solution. That's why we're here. I just talked about that. Okay, so materials, and I think we're in the home stretch. So I don't see anybody sleeping yet. I guess I'm doing okay. All right, so we talked about this equation again. So now we're going to go at the K factor, and that's what we call, what I call the process factor. We'll talk a little bit about the kinds of photoresist. I alluded to this a little earlier. Positive tone, negative tone, materials, various, formulation changes that were driven by the wavelength. Hopefully not too much chemistry to make you glaze over, but enough so that you can at least understand what goes into the process. Okay, so we talked about the photoresist. I told you that it had a polymer, a sensitizer, that's the light-sensitive agent, and a solvent. A lot like paint, right? Solvent and paint, spread it thin, it dries, it evaporates, same kind of thinking. So we also use a layer under the photoresist, which we call a bottom arc. Now, your professor told me that when you were coating your wafer, you started seeing funny stuff at the edge. Well, sometimes that's a surface issue. Surface tension, surface adhesion, surface wetting, right? And you know, when you do painting, if you had to paint a red wall, have you ever painted a wall with white paint and all of a sudden you still see the other paint through the wall? Have you seen that? Is that just a way of getting around that is primer. Put a primer down, boom. Then you put your paint on it, 2 layers of paint, knocks it out. Seen it before, right? Yeah. Same thinking, right? We put this layer down, it makes it so that the next layer can stick to it, because in chemistry we learned likes stick to likes, right? If you want to dissolve something, it dissolves in something that's like it. Oil and water don't mix, but salt and water, because they're both ionic, mix, right? Okay, so same kind of process. We put that layer down, that layer sees the wafer, your resist sees the bark layer, so it sticks to it. And we use that because it helps us with reflections from the substrate. These are shiny substrates, right? If they reflect light, they expose the photoresist where we don't want it exposed. That's a problem. Then we also have arcs that we put on top. You might have heard on some things they have these anti-reflective coatings. This is kind of an anti-reflective coating for the photoresist. We actually have those on some of the chambers inside the scanner because we don't want light bouncing around the scanner and hitting the wafer where we don't want it exposed. Developers, that defines the pattern, right? After you expose it, you got to somehow clean it out, so you use the developer to do that. Just like photographs, right? Developer. Back in the old days, take the picture in the dark room, you got to stick it in the developer, then you stick it in the fixer, right? Developer. Nothing changes. Oh, it's the same stuff. And then we have these other things we call ancillaries. So I mentioned if you get some stuff on the backside of the wafer, one thing we also do is we wash the backside of the wafer sometimes in the tool. Or we don't want it, when we coat the photoresist, it looks great. You look at that wafer and say, oh yeah, you spin it on, it just spins off. Well, you know what really happens? You spin it on and sometimes some of the junk goes over the edge of the side of the wafer. How do you get that off? Well, we do what we call edge bead remover. We have a solvent going around and it cuts that off in the tool. The tool puts some solvent around the side and it knocks off that stuff from spreading around the edge. And then we'll do it on the back edge too so that it's clean when it goes in the scanner because we don't want those hot spots. We don't want those particles on the backside of the wafer when it goes in the scanner lifting the wafer up. So backside clean. And those are ancillary materials. And then adhesion promoters. That's what I mentioned. Sometimes when you're coating on a wafer, that's a surface that photoresist doesn't want to stick to. So you put an adhesion promoter down, and then you can apply your resist and it coats uniformly on the wafer. And the other thing about that, if it doesn't want to stick to that, one way you can beat that is by putting tons of photoresist down. But now you're talking bucks. If you put an adhesion promoter down that's cheaper, and then you apply your photoresist, you can use less photoresist, so it saves you money. All right, here's an example of what's going on in the exposure process, right? You have your photoresist coated wafer, that's resist on top in red. Here's your mask, You expose the light through here, it changes the chemistry. You know, that active agent becomes activated, right? I have the purple area. Now I want to make my pattern, so it goes through a develop step. You usually do a bake or something here. It goes through this develop step, cleans it out, right? And in this case, where I exposed stays. So that's a negative resist. And typically a negative resist, where you exposed it, it cross-links, or the molecular weight goes up, so it dissolves more slowly. That's a negative resist. I differentiate that from this, the positive resist, because there, what you exposed goes. So the mask blocked it. You exposed over here, so that area is developed away. That's the positive resist. And what happens in these things is, I mentioned that bias. So when you expose here, what tends to happen is, as that arrow is pointing in, that feature gets chewed in sometimes, because sometimes that light, it dissolves, and that chemistry really isn't very selective at that edge. So you get what we call a bias. So maybe you were trying to print a 1 micron line, you print 0.95. But if you got plus or minus 0.1, you're okay. But still, it wants to get smaller that way. So these things tend to be smaller than you want. A negative resist is just the opposite. When you expose it, it wants to keep growing. So sometimes you get a bias going that way. So it helps you. Because the next process is etch, and etch chops stuff off, and if it's already small, it makes it smaller. If this thing is big, you chop a little off, now you get back to the size you're supposed to be. So there's all kinds of games you can play. A little busy chart, but I just wanted to show you a number of the applications we use photoresist for, right? Here, we use it to etch into a substrate. So in this case, the oxide, remember I had that gate in the first part of that MOSFET? And we etch the oxide, this is how we do it, right? We block it with resist, we protected the oxide, we etch this area where we don't want oxide, we strip off the resist, we have oxide, space, oxide. Preferential oxide. Here, we have resist oxide all the way over, we want to do some implant. So we etch away the oxide, we can implant there with some active ions. You know, this is a different kind of circuit, not a metal line. And so this is where the implant would go. We strip off the resist, we can strip off the oxide, and we have that implanted area that we can further build on, or we could do the gate, right? We did the implant, we stripped the resist, we put our gate level up here, and we're good to go. Another process, because we're kind of creative folks like this, we have this bad image that we printed, and that is a bad, I didn't mean that. I don't think I could do that again, make that, the word look like that. But anyway, I digress. But anyway, in this case, what we want to do is we have this bad image, right? I told you we usually want slab technology, but here we don't get the slab technology. We get this retrograde profile. But it's useful, because what we can do is deposit metal on top. And the metal goes down in there, and then it leaves that space, and where there's no resist, we can put metal. Then I can take my lift-off chemical and lift off the photoresist, and I get metal line. Sexy. So this is actually a process used in manufacturing. Somebody made a lot of money off this. But, okay, so nothing is garbage. You can always find a way to use it. All right, so we talked about the chemicals used for making materials sensitive at the different wavelengths. I like this plot because there's a lot of data in this plot. For example, I told you about the resist maker's holiday. That's here. Diazoquinone, we use the arc, the mercury lamp, as Andy was talking about, and then we went over to the lasers. This is indium carboxylic acid, undergoes this chemical change, right? We expose it to light in the presence of water. It gives off nitrogen and this base-soluble chemical, and that's why we use KOH or tetramethylammonium hydroxide as a developer. Likes dissolve likes. So when I expose it, this area of the photoresist is now sensitive to that base developer. The area that didn't get exposed is not sensitive to the base developer. And this system is even better than that, because when it does form this indium carboxylic acid, we have diazo coupling. This thing goes back and attaches to the polymer, and now the polymer is even less soluble in the developer. So we got kind of a, I won't say amplification because we use that for the car resist, but I would say an enhanced solubility inhibition by using the diazo. So this was a wonderful material. The only problem with this stuff is if I took a boat of wafers with this and walked outside, when I got in the lab, it'd be all gone. It's sensitive to white light. So if it was here, any of these lights would expose the entire wafer. I wouldn't get my differential printing. It'd be all gone. Got to be careful with that. Keep it in a brown box. There you go. So, I'm sorry, a little faster than I wanted to go. So why did we move away from these kind of materials? Because they were great. What was great about this is they weren't sensitive to base environmental contamination. They were very insensitive. We loved them. Mask makers would print plates, masks with this, ship them to Japan, leave them on the shelf for a month, take them back, process them, and get good results. You can't do that now. These were great materials. I loved them. They were useful down here. But what happened was the resin that we used, called Bakelite or Novolite resin, this will help you for a little context. Airline plane brakes use Novolite resin as the material for the braking. So there's a little reality for your life. Anyway, this thing has a high absorbance. Why is that a problem? Well, I need the light to get through the film to convert this material so that I can develop it. And because we were using this Novolite resin, notice it absorbs very low down here, not much absorbance. But as soon as we got down into this deep UV area, wham! You're getting zero light at the bottom of the film. We made use of that too. We called it top surface imaging. We were able to image in the top surface, silate it, and go do some other processing. We made a process out of it anyway. Like I said, nothing ever goes to waste in this business. But in any case, we couldn't use it for single layer printing anymore. We had to transition to another material. So this is kind of the evolution, right? For contact printing, we got away with these diazo material, and actually in the beginning, it was these cyclized rubbers. They were negative tone materials. We developed them with solvents, xylene and stuff like that. Bad stuff, stink. You know, not really stuff you want to use in a fab because they're very explosive, fire producing, so on. We don't want that. 436, as I mentioned before, we were able to start using these diazoquinone materials, right? Or where were we? I don't see the diazo. Anyway, the diazoquinone, which I showed you the last time, was usable from here to here for these 2 generations. And really, there's a 405 that's not shown here. So we got 3 generations out of that. Then we had to switch gears to the chemically amplified materials. That's this. And that went for the 248. And then what happened was that 248 resist, which was great. Actually, the guy that originally came up with, one of the guys, there was Hiroshi Ito and Grant Wilson, that came up with these materials. He got the Medal of Science from the president, from George Bush, for coming up with the chemistry to do this work. So that's a little piece of history for you. That material was only really usable for 1 generation. For the same reason, the polymer in that absorbed too high at 193. So we went to these aliphatic looking materials, low absorbing, but this is kind of what we're doing now, these mixed polymers now. And that's what we use because of the transparency at 193. So this is a little bit of chemical amplification resist that I wanted to talk to you about. I mentioned before that this thing had acid, right? And let me just help you a little bit here in a different way. Where did this chemistry come from? Because what's old is new again. This chemistry came from actually pharmaceuticals. In pharmaceutical chemistry, a lot of times you want to take a chemical or a medicine and you want to do some work on it, and then you want to change it back to what it was originally. So we put protecting groups on. So this group that you see right here is called a T-butyl carbonate. It's a protecting group. It's put in that area intentionally because we're going to strip it off and we want to come up with that. And it's a hydroxyl group. And we know from diazochemistry, when we went to the Indian carboxylic acid, we were able to solubilize that in developer, organic developer. And we like that. It's not flammable, it's not explosive. It's, you know, if you get it on you, you just wash it off. You know, it's really easy to handle, and it's very preferential in this process. Organic developer is not going to touch that, but it's going to develop the nonsense out of this. And the other thing about that is that CO2 helps us, because if you expose something and you generate a gas, the gas comes off, what do you get? You get holes. So if you get holes in the area where you're exposed, oops, I keep doing that. What happens is the developer is able to penetrate the film better. So this thing had accelerated development because both of these gases would leave the film, and now all of a sudden developers coming in and had a place to go. It could go in where the gas left. So it develops like crazy, and that's very good. We like that. Fast development, fast throughput, get it out fast. These resists are very fast. The acid that was used for this is right here. It's called the triphenylsulfonium trifluorate hexafluoride. Very strong acid, very strong. And the reason why it absorbs so much is these rings catch the light, generate the trifluoric acid, goes off and attacks this group, cleaves these, out go those gases, generates that, developer comes in, cleans it out. What's interesting about this material, and I kind of talked about it a little bit, I said that when you develop this in KOH, for example, we don't use KOH for this, we use tetramethylammonium hydroxide, but base developer, it only attacks here. So the area that didn't get exposed doesn't get touched. Now, if you take this film and you develop it now in xylene, which is an organic solvent, or the solvent that the photoresist was made in, PGMEA, for example, it would dissolve this, but it won't touch this, which is polyhydroxystyrene. It's not soluble in it. So now you can reverse the tone with the same resist system. This can be both a negative and a positive resist, depending on which developer you use. That's very useful, because if you're in a fab and you have resist A, resist B, resist C, a lot of times what happens is Supertech uses the wrong resist for a particular application. Now you got a bad wafer. Happens to the best of us. If you have one resist and you're using it everywhere, it's kind of hard to make that mistake. If you're using one developer and you're using it everywhere, same thing. We used to have a lot of different developers back when Andy and I worked in IBM Burlington. We'd have all these different developments, and I was a photo engineer. I was getting called up, hey, all of a sudden the resist is too fast, blah, blah, blah. I go, okay, so how do we process it? Wow, we used a regular bake, and we developed it over there. Oh, okay, yeah, wrong developer. Should have developed it over here. But sometimes you spend hours getting to the bottom of that because, of course, nobody would remember that they developed it in the wrong place that quick. You'd have to go work it through. So when we went to one developer for everything, kind of helped us out for a lot of stuff, gave us a lot of flexibility. So here I was talking again, likes dissolve likes. So remember the polymer had the OH, and look at that, TMA, and it has an OH, tetramethyl ammonium hydroxide. KOH, KOH. Likes dissolve likes. Remember that. Likes dissolve likes. Very important thing in chemistry to remember. So, and I told you that xylene would dissolve the other stuff. If you look at xylene, actually anisole in this case and xylene here, it's all organic. Well, if we go back to that other one, so was that. All organic. Likes dissolve likes. It's a simple game when you think about it. Okay, so with everything there's some problems. Everything isn't perfect. So we do some imaging, especially back when we were doing IG and H-line, we had this effect called standing waves. This is the photoresist edge. That's the way the light looks coming in. Problem. Couple approaches to fix that. One thing we did was we would just elevate the bake. We just bake it at a higher temperature. So maybe the post-applied bake or the post-exposure bake that we were using here was 100 degrees. If we took it up to 125, we could smooth that edge. But we also got a little bit of a slope. It would flow a little bit. And sometimes the chemicals that we were using would break down in the higher bakes. But once in a while, you could get away with just doing a higher bake to get rid of that problem. For example, in this Shipley material. Another solution was those bottom anti-reflective coatings I told you about, which we show here. Here's the standing wave phenomenon. This is with bottom anti-reflective coating on it, and notice we don't get those. And we didn't have to do the higher bake. So the standing wave was caused by this effect. We call this the swing curve. What this is saying to you is, as I change my thickness, my resist sensitivity would change in the cycle. And notice it's an increasing, right? That's a problem. That says if I have any variability in my coater, when I expose it to my photoresist, it may or may not clean out. Well, that's yield loss. That's not good. This red line is the anti-reflective coating you put on it. Look at that. That swing, what we call so-called swing ratio, is reduced tremendously. You can live with this. Do a little overexposure, you're always going to get clean out. So this was a great accomplishment by this company, Brewer Science. They really have the cornerstone patents on this. It's a little dinky company. The guy had made himself a nice little company out of just materials to coat on the bottom of photoresist. And actually, they also make spin coaters that are, not really high tech, but they get the job done. So there's an opportunity for entrepreneurs too. That's just the layout of a whole. I just wanted to show you some patterns of a whole bunch of images together. So the other thing is, I told you about top arc. This is an anti-reflective coating you can put on top of the resist. Same kind of thing. You see up here where you had the swing ratio we just talked about. You put this top arc, and if you look at this, the red line, it's actually out of phase. When this one is down, this one is up. Here's another thing. Calculus? Calculus? Okay. So when I have a function like this, when I take the first derivative, what happens? What's the first derivative? Should be 0, right? So here, if you take the first derivative at this point and at this point, that's where you get your 0 points. So when we're in the fab, what we do is we operate there because any change is 0. It's not changing. If I pick a point here, it's changing, right? But if I pick a point there, I have a flat spot for a while. That's where the slope is 0. That's your first derivative, right? So, that stuff that you're learning, it kind of does get reapplied sometimes. All right. So you see that some of the problems that we had too was we'd have these things like mouse bites. I want to hit the right button this time. Okay, mouse bite. See that? You know what happened there? You have metal under the bottom, light came in, and it reflected right through the photoresist. So the photoresist did what it's supposed to do. Where you exposed, you get a pattern. It's a hole where I don't want it, right? So I told you that straight light thing's a problem. We put that Aquitar on top, and because it flattens out this effect, I don't get that problem anymore. But you can see we got a little standing wave phenomenon. You can still see it. And now I have yet to have a device guy tell me why that's a problem. Okay, anyway. Let's talk mask a little bit. That's the K1 factor in that equation. Here's a mask. You see him there? Here's a picture for you. I love this picture. Okay, mask. Just like we can play games with photoresist, just like we can play games with the scanner, we can play games with the mask. And what games can we play with the mask? This is kind of complicated. Andy told me people would be glazing over now. I'm happy to see that all the faces are still looking. You're not glazed over yet. Andy was wrong. Anyway, he's glazing over though. He's sliding down in the chair. Okay, so when the light comes through, this is a typical binary mask. This is the mask like these that we're using right now. The light comes through, no funny business. Light comes through, it makes this signal, right? The pattern in the photoresist looks like this, and then guess what? The pattern on the wafer, it looks like that. Where's my lines? They're gone. That's a problem. I need lines, right? I'm trying to make stuff. So how do we get there? We can get there a number of ways. Phase shift match, the mask, which we get to by these three approaches. Approach one is what we call putting a shifter in there, right? Notice that when we expose through this, the light goes through here, we get some leakage of this light. So when we go down here, it gives me some help on this edge. So this edge that I'm trying to print gets some help from here. So I'm getting really double dose here. And so the signal that the wafer sees is that, and then the pattern I see is that. So this is the signal I'm always trying to get at the wafer surface. The trick of getting there is this. I put this kind of transmissive film here through the mask that allows light to leak and help me over here when it gets reflected. So I get a higher amplitude here, and then I get I get the nice pattern that I want at the wafer surface. So it's the same game here, but I can play it a different way. I can etch the chrome, right? So here, I've etched the chrome a little deeper. Here, I have the same chrome. So now that these two are at different intensities of light, when they go through, they reinforce, right? And then I get this kind of signal. Now, I got a little noise there, but that's not going to print. And then, lo and behold, nice patterns just like I want it. And it's the same thing here, except here, what I do is this is called a hard shifter. I put a chrome piece here that does the same thing that those do. They give me that higher intensity, just a little different. Notice that the waveform is a little different, but the net result, the same. So there's a number of ways of getting that phase shift character to create that signal that you want that gives you the patterning that you want. So the key to recognize here is that this is very small feature printing. You can see if I use a regular mask, I get nada. If I use these phase shift masks, all of a sudden I'm able to pull them out. And this is just showing you the process improvement with phase shift mask. Blue is without, right? You can see there's definitely an improved depth of focus, and there's also an improvement in the resolution. Okay, new innovations. Kind of talked about this a little, and you know what we used to do is we would turn one knob and go like heck with that one knob. Then we turn that knob. All right, let's turn the knob in the middle, photoresist knob. Turn that knob, okay. Then we go, okay, mask knob, let's turn that knob a little bit. Okay, scanner knob, let's fool around with that. Now we're trying to tie them all together. And that's what's happening here. This computational, you're trying to get right down to the pixel that goes into defining these patterns. And what we do is we can print, sometimes when we're printing a line, the end of it won't print because it's near another pattern like that. When you have two type lines like this, they don't print. What happens is this guy sees more energy at the edge than this guy, and so this guy prints smaller and this guy prints the right size. Well, you want them to print the same. So they need to think that they're both seeing the same environment. The way we do that is sometimes we put features on the mask that don't print, but the light thinks that they're going to print. And so that ultimately we get the pattern we want. So the ideal pattern that we want would be here, this squares. But because of the games that we played here and with the optics, which I showed you before, right? The dipole, the quadrupole illumination, you tie those all together and you're able to make an image that's reasonably close to what you want. Not ideal, but close. And at this point, that's acceptable. We can use that. So we do that by controlling the mask and playing some games at the light source. Same thing here, only it's a much more complicated, and you can see that from here. It's a much more complicated to make a much more complicated pattern, but it's all the same game. It's playing what you can do here and tying that together with the optics, and you'll hear a phrase batted around: source, mask, optimization. Source, mask, and we're optimizing them so that they work together to give us the result we want on the wafer. Okay, that's all she wrote. There's still a lot I didn't cover. I didn't talk about how we print the mask. That's a whole nother thing. E-beam lithography, things like that. I didn't really talk a lot about what we're doing right now, multiple patterning, right? But you guys can invite me back and I can do that. All right, thanks.
All right, so we're running a little bit.
Oh, sorry about that, Andy.
But
you want me to do it?
yeah, I'm doing it. So what we got is we got about, give us 2 more minutes and we'll
wrap it up.
Be ready for Q&A. So again, hopefully you see why we study science, why we study math, why it's an integral part of the program. Well, what I wanted to talk is how the NEATEC program, the National Science Foundation grant, and College of Nanoscale Science and Engineering interact with each other. So, you know, one of the things I've been working with the SMT program here at HVCC since 2006, when I actually hired one of your alumnus into our, Sandy Finke, the infamous Sandy Finke. We hired her into our clean room out of this program. And since then, you know, I've been involved with the SMT program, as well as the Industrial Advisory Board for the NEATEC program. But how do we do this stuff? So I'm just going to, real quick, what NEATEC does is it takes this concept of silos. you know, the kindergarten to 12th grade school district, and your undergraduate programs, your graduate programs, and your community college programs typically would act in a silo. You know, they're not communicating with one another. And so what NEATEC is trying to do is to take these silos and kind of make them interact with each other. You know, kind of communicate, kind of support one another. For example, you know, we have this relationship with, CNSC has a relationship with Schenectady Community College. It has a relationship with Hudson Valley Community College. We're trying to drive curriculum changes into the grade schools, and then have that all support College of Nanoscale Science and Engineering. You know, for example, you know, we're starting to work in Schenectady County School District, actually having curriculum, taking classes in 10th and 11th grade that prepare you for what you're going to study at Hudson Valley Community College, what you're going to study at Schenectady College, Community College, and then this would support what you would learn at College of Nanoscale Science and Engineering. You know, beautiful facility over at CNSC. You know, NEATEC kind of links the industry with community colleges, educational partners, and the federal and state government. This whole thing that, you know, industry tells NEATEC what they want the students to learn, and NEATEC is kind of like at the center of that discussion. It's ensuring the curriculum exists to adequately prepare you for jobs in the private sector. So this is probably the one thing I want to take away. We're already using Hudson Valley Community College students, Fulton Montgomery Community College students, Schenectady County Community College students. They were actually serving as interns within the clean room. I think in 2011, 2012, we actually had 8 interns from a variety of different community colleges. 6 of them worked in the CSR, or the Center for Semiconductor Research over at CNSC. 2 of them actually worked at Semitech in the FEP program, doing basically doing electrical tests on wafers that Semitech was producing. So, you know, these guys are actually working as technicians in the semiconductor industry as part of this intern program. If you get an opportunity to do this, highly recommend it. You know, internships are fantastic opportunities both for you as a student, you as a potential employee, you as a, you know, it's great for the college, it's great for the industries that get a chance, you know, to see if they like you and to see if you like them. I've literally had people we've hired that came to work at 7 o'clock in the morning, went into the clean room, put their suit on, and left at break and never came back. You know, I mean, you know, not a good relationship. However, when you know what you're getting into, you know, I always find that the time in the clean room really goes quickly. You know, it's just I don't know. My theory is that it's the suits are the white suits, the clean room garments are slipperier, so we pass through time quicker.
Oh,
so that's just my theory. I've not been able to. I was going to try something with a watch one time to see if it's changed at all. But again, good place. It's good work. Good place to be. And again, CNSC, Semitech has opportunities through the NEATEC program. For example, you know, we're projecting to have in 2015 32 technicians, mostly supporting the new NanoFab X building, as well as increased presence at Semitech. So again, there are opportunities in the internship, and I don't know. I guess Abe is the proper contact to explore these. Hey, you get paid. It's, you know, it's 20 hours a week. It helps out. It helps us out because you're not going to work the most desirable hours, but it gives you good experience. It gives you a chance to see, is this what I really want to do for the rest of my life? And again, and you get yeah, exactly. All 8 technicians that went through the program initially all landed jobs. Some at CNSC, some at General Electric. I think 1 at Global Foundries. There's something like, we're going to have a shortage of something like 1,000 technician jobs in the Capital District within the next 2 or 3 years. Lots and lots of opportunity here. We can bring them in from California and Texas, or we can grow them here local. as part of the NEATEC program. Again, the whole idea is we're trying to take this beautiful facility on, this $14.8 billion facility that's been constructed by the combination of New York State funding and private equity, and we're trying to create, programs that support one another. Again, you can literally come to CNSC now and go from an undergrad program to a PhD level program. You can take classes at Hudson Valley Community College. All of these things are like pieces of a puzzle that kind of link together to adequately prepare you for the opportunities and the long-term employment possibilities that exist here up at Global Foundries. Everybody's heard about the new potential TSMC fab that could be coming here, another couple, 4,000 or 5,000 jobs. I mean, lots of opportunity in semiconductors in this area. And I think that is it. Thank you very much. We kept most of you here. Thanks. So there's a little show and tell up here if you wanna.
Also, I want to add about the internships. Yesterday I was talking with Dr. Gia, the dean at the CNSC program, and very soon we are going to do a dual internship. Half of the time of the internship will be done at CNSC, and the other half with Global Foundries. We are talking with Global Foundries to see if we can provide half of the time at Albany and half of the time at Global Foundries. So, and this is all. That's why we need the student here at Carson Valley and Fort Montgomery and Mohawk Valley as well. Okay, so you young people, you will have a lot of opportunities for the rest of your life. I think this part of the world will be all the time full of fabs. Okay. Okay. Do you have any questions to the presenters?
So yeah, if you got a question either for myself or for Warren.
I have a quick question. We always see a lot of manufacturing talked about, but I was just curious about recycling. Do they, is there like plants that recycle the chips? Or is it cheaper just to produce wafers than recycle?
Well, for example, in the manufacturing process, we have, there's some fallout. If you break a wafer, for example, we have a bucket that we throw this wafer into because it's sharp, breaks into a lot of different pieces. Now, the volume of silicon that we generate, like as a waste stream, is pretty small, pretty low. Now, I remember when I was back at IBM in Burlington, we used to sell the broken wafer pieces, and what they would do was because they're somewhat reflective, they would actually grind them up and then put them in paint. And the paint on the roads has this pigment in it that's crushed up silicon wafers. But there is recycle projects. There's reclaim projects. For example, there's a company called NEATEC down in New Bedford, Massachusetts, and we send wafers down there. And what they do is if we make a mistake and we have a wafer that's a typical 300 millimeter wafer, according to the SEMI M1 standard, 775 microns plus or minus 10 microns. So if we make a mistake, I mean, really all the processing is done and the couple is really built up on top of this substrate. So if you make a mistake, you can literally take this wafer, send it down to New Bedford. They can actually strip off, they're going to take a little bit of the silicon with it to reclaim it, but then they polish it back, and then you've got a wafer that's maybe 773 microns thick. And you can reuse it. Now, you might not use it as your prime device wafer that's going to become the Pentium processor, but you might use it as a test wafer, and then using it to spin resist on to measure the thickness, on a sacrificial wafer. So there are some opportunities to recycle. Now, products.
So let me just, the other thing is what's happened recently is these recycled wafers are being used by solar.
Yes.
And a lot of times what we don't use, the broken wafers and so on, get sold, right now they're getting sold to Asia. These guys take them and they make solar chips, solar panels and things out of it. So they do get recycled.
Literally, you take this wafer, you scrape off all the stuff that's on top of it, you melt it, and you make a new wafer out of it. Because it melts at 1180 degrees Celsius, and you can make a lower grade wafer. Yeah, so there are some opportunities to recycle. At the college,
Yeah, we're not. Well, we should differentiate. He said manufacturing, and really we're not manufacturing, right? What we are is really development. So as Andy said, our volume of wafers is low. We do recycle things like the chemicals. Those get recycled. Clean room suits, I'm understanding, are getting recycled too at this point. But for the most part, what we use is pretty much consumed or recycled as chemical, or it's just waste.
it's a good question.
As an intern, what are some of your jobs as an intern to do at
Well, like the example of the Semitech job, it's you're taking wafers and you're actually testing electrical properties and recording that data and and relating it back to the process steps that create it. So there's some time in the clean room gathering wafers, taking those wafers out of the clean room and putting them on test equipment, and actually studying the electrical properties and recording that data into a format then that the engineers responsible for that process can use. The CNSE jobs are every area of the clean room factory. It's basically moving wafers.
Processing wafers,
Yeah.
exposing wafers, developing, etching, could be any of that.
Yeah.
Measuring.
Yeah, so I think again, your CNSE opportunities are very broad. The program here is very broad. It's going to teach you a little bit about everything, but then when you actually go to work in the area, you're going to be specializing in a certain area. For example, you might be a photolithography guy. And oh, by the way, Warren forgot to tell you the most important thing
That's right.
to know when you are working in photolithography. And what is it, Warren?
It's always etch's fault. All right? It's never a litho problem. It's etch.
Yeah.
Or CMP sometimes. Those guys slip up too.
Yeah. Okay, so just remember, for the budding photolithographers amongst you, if you take one thing away from our talk today, please remember that. It's an etch problem. Always an etch problem.
I'm surprised that we didn't get the one question, which I would have asked. Okay, I'm sitting here, I'm listening to you guys. I want to know, how much money do they make?
Yeah, good question.
Yeah, I mean, why should I go be an intern? I mean, why should I be a technician? How much money do they make? Right? So I was thinking about that, and I was thinking, what's the average salary for someone? Because I remember Albany when it was the Albany Airport. You drove up here, and it used to be a place you drive through. You don't stop. Now this place is a mega complex. And I remember reading an article that had Dr. Calieros on it, and he was talking about a couple graduates that we had in the PhD program. Those guys graduated, and they were making $90,000, $100,000 a year. And I bet right now, let me think about it, probably technicians are $50,000, $60,000 a year.
Probably 50,000.
That's not bad, right? I bet the average salary around here is probably that. The average salary is probably $50,000, $60,000. You get out as a technician, 2 years education, you're making that. Maybe as much as your dad, right? And then if you go on, wow, the difference between 50 and 100 is quite a bit in your career. So I think you guys are doing the right thing. Yeah. I mean, you're catching the wave, right? All of a sudden, this place is taking off, and you're in it. You're already schooling yourself to be ready to ride that wave up. It's a great opportunity for all of you.
The other thing about education, in the education, we showed this kind of puzzle of all these different types of education that you can achieve. And at the top is the PhD. To be honest with you, I think the top is the technician. I mean, I would, and I've said this before at different meetings here. I'll take a good technician over a good PhD any day, because you do more. We're going to get more work out of you. Again, all apologies to the PhDs in the room, but again, our industry is based on. I mean, you guys will have jobs that are the most, in my opinion, some of the most important jobs in the factory, because you guys are doing the work. You're moving the wafers. You're getting the data. And there's just a tremendous amount of responsibility that comes with being a technician in the semiconductor manufacturing world.
So
A lot of
says
responsibility.
This. Andy says this. Have you ever been a technician?
No.
Okay. I was a technician. When I started my career, I started as, I didn't even have a degree, right? I had a biology degree, and when you go into a factory like this with a biology degree, they won't make you anything. You're barely a technician, right? I had to go get my chemistry, by the way, Dutchess Community College, Poughkeepsie, New York, right, where I got my chemistry degree. When I got that, I got to be a technician in Fishkill, and I started working in the fab. Now, technician, great job, and I was a doggone good technician, right? I always got good appraisals, they love me. But you know, money, right? We're all working for money. So I started out as a technician, it was great training. I know inside the operation that there were times where on third shift, I was running the operation because there was no engineers around in the off shift. So technician, very valuable. I wouldn't say that you aspire to that, because what happened to me is I went on and got my bachelor's degree. I went to Marist College, got a chemistry degree, and I got a business degree, but that allowed me to become an engineer. And when I became an engineer, the world opened up. I've traveled everywhere. I lived in Europe for 2 years. I've lived all over the country, Washington, California. I'm back in New York, haven't left here, okay? The opportunity to go and see other parts of the world, I mean, last year I think I was in Japan maybe 10 times, right? I mean, it's just an awesome opportunity. I mean, Andy, he got started in this industry. He's been in Vermont, Texas. It's taken him everywhere. So it really opens the world up to you. There's an opportunity. Yeah, you're going to start such and such a place, but you never know where you're going to end up. And it was all afforded by getting this education. You know, why did I had a family when I went to school. Why did I do that? I went to school because I wanted to be able to make I didn't want somebody to tell me, you can't have that job because you don't have X. So I went and got X. So now that's out of the way. Now if I show I have the skills, I want X. And I got it. So I'm telling you, you have an opportunity now to work your way from where you are. And, you know, technician, great. It's wonderful. It's a good place to start. Aspire. Keep going. Let the next guy have the technician slot that you had, right? But just keep moving, because the sky's the limit, right? You get in, you drive. This is the entry point. You keep pushing. You know, I don't say, I agree with Andy. I've had lots of PhD guys working for me, no offense. Higher value people are usually the guys that work their way through and got their bachelor's and so on, right? Because those guys are hungry. Be hungry.
In my perfect world, when people actually, when engineers and PhDs come to work in the semiconductor industry, I think it should be mandatory for them to spend 1 year as a technician.
I agree.
And do the things that technicians do, so that because they're going to be a kinder, gentler, and more productive engineer as a result of that. Because
well,
of
where
what
the rubber meets the road too.
Yeah.
If you know, like when I talk to people, and I'm talking to people that work for me and they're in the fab, I know what they're doing, because I did it, right? Yeah. There's nothing like that. A lot of people come out of school, and if you don't really get in the trenches, you're up here, you don't really know what's going on down there. You have a theoretical idea. But there's nothing like actually being in there, doing it, understanding what it takes to get it done. To make you, I think it makes you better. So I agree with Andy.
So do we answer your question adequately?
Yeah,
Oh, he's back up.
I just got another question.
Oh.
When you said it, you have to be hungry. Does the hours as an intern allow you to eat, as far as going to school and getting more knowledge? What shifts are available for an intern?
So the way that the NEATEC internship program is structured is it's weekends and nights to allow you to minimally interfere with school. So you go to school during the week, and then maybe Friday, Saturday, Sunday you're working, or Sunday, Monday you're working. Excuse me.
That's a good question.
Yeah, so the program is designed so that you don't have to quit school to go to work as an intern. Yeah.
And if I could just say one more thing, when I was going to school at Dutchess, I was lucky enough to be part of I was in the chemistry program, to be part of their chemical program. They had an internship with IBM. And I went in their internship. I worked at IBM, so in the summer, I got to work full-time. And during the semester, they liked me. I worked in the environmental lab doing analysis of smokestacks and water pollution and stuff like that. It was a great job.
I did that job in my internship in Endicott.
Okay, so yeah, but I got my permanent job at IBM. I'm 15 years IBMer, right? I got my job out of that internship.
Yeah.
I did it for 2 years while I was going to Dutchess, and then when I graduated, they hired me.
Yeah. Similar story. I worked as between junior and senior year, I worked in the environmental engineering department at IBM in Endicott, New York. Smokestack analysis, stack analysis,
Yep, the
lab
bubble
reports.
meter. The bubble meter.
Yeah, yeah. Yeah, I didn't know you did that.
No, I did those things.
Yeah, I've known you for over almost 30 years, and I
Didn't know that.
But again, I really credit that internship with introducing me to the manager who ended up hiring me and starting me on my 17-year career at IBM. Yeah. And Semitech and IBM are related, you know, so really, if it wasn't for that internship, I wouldn't be sitting here in front of you today. Internships, good opportunity. Try to see if you can get into that program.
Yeah, and to add to it, NEATEC through CNSC, we are going to increase the number of interns starting in the fall. So there is a lot of opportunity because, like this gentleman say, an internship means a secure job, almost secure job, unless you do something big. So.
Yeah. But and the other thing is that it also will help pull all of your classroom work into focus. I mean, you'll really understand, you know, why we study science and math.
Yeah. You have a question? Yeah.
I just had a question about the manufacturing process.
Sure.
We're learning that silicon and germanium are the best semiconductor materials. A few months ago, I read that there was research being done with iridium gallium. Is that anything you guys are using over at CNSC?
You said iridium. I know that there's
Iridium gallium.
I know there's some research being done with ruthenium, and there is some germanium interest, but no. We are really focused on silicon right now and 3.5. That's the 3.5 on the material table.
Mm-hmm. Okay.
We're really focused on that. What you're talking about is even further back. So remember that the impetus for that organization is companies pooling to work on next generation. So really, you have to focus on some things. We're focused on EUV, we're focused on 450, and there's a little bit of interest going on alternate materials.
Okay.
Any other questions, guys?
Okay, we have some food for lunch, and remember the school is closed at noon today, and I want you to take lunch and have lunch here and drink safe. Okay, and let us give a good applause to our.